Here we also it also tells you that the amplitude of the E field and the B field should satisfy this relation, which means that this EM and this PM is this amplitude, the amplitude of the E field and the amplitude of the B field of the EM wave. So this is EM, this is BM. They should have a fixed ratio. They cannot be arbitrary ratio. This fixed ratio is actually the speed of light. EM over BM should be C. Okay, I will try to tell you why it will be this ratio after this, after the slides of this chapter. Yeah, so try to accept it is correct. I'll show the proof later. Okay, so here we also introduce another variable called the pointing vector. Pointing vector. Okay, so the pointing vector is actually the rate per unit area at which energy is transported via an EM wave, and this pointing vector is given by the pointing vector. So actually this is the pointing vector S. Pointing vector is denoted by S, and of course it is a vector. And for this is a vector, so it should have a magnitude and also the direction. The direction is actually the propagation direction of the EM wave, so no problem. And as I mentioned before, the direction is actually E cross B. And so E cross B already determined the direction, and it should multiply by another factor, so that it is actually the pointing vector, the pointing vector. And then the amplitude refers to the rate per unit area at which the energy is transported. Okay, so so here it should be multiplied by mu naught over 1 over mu naught, 1 over mu naught. And let me see. I will also show you why we need this factor, why we need this phase factor later. Is actually related to the energy density. The energy density of the stored in the E field, like this, 1/2 of epsilon naught E square. It is one result in chapter 25, chapter 25, and also UB is 2 mu naught and then B squared, like this. So this is the energy density stored in the B field. We study in chapter 29 or 30. In chapter 20, I'm not really sure. Chapter 29 or 30, maybe 30. Yeah. So actually, this is related to this stuff. Okay, so actually this is a pointing vector, and so the main idea is we need to know, this is the direction of the propagation direction of the EM wave, and also the amplitude is the energy per unit area. Okay, and here it introduce another variable called the intensity of the EM wave. The intensity. So there is a equation like I equals E RMS square over C mu naught. And as we have mentioned, as much as the E is a sinusoidal, so EM is the amplitude and the RMS value is the amplitude over square root of 2. Okay, also here it tells you that the intensity is actually the power per unit area. So this is the power generated by a source here, so it will start to propagate for in any direction, in all the direction. So for example, for the first moment, it transmits up to here for delta t. For delta t, it transmits up to here, and of course it is a sphere rather than a circle. But yeah, here we just draw the cross section. So for here, suppose this is R, so maybe this is R1, R2, R3, R4, so on and so forth. So this is delta t, and then for another delta t, it transmits up to this sphere, and then for another delta t, transmit to another wave front. We call it wave front. Okay, so as much as this is a sphere, so the surface area as, or maybe you can write it as A is 4 pi r square. So actually the intensity is the power generated by here and then transmit up to different wavefront at different moments. So PS over 4 pi r square. So in that sense, yeah, so actually the I means, suppose you have a detector here, you try to detect the intensity of the source. You only sense the energy at this small area only. You cannot sense for the whole sphere. You can only sense here. So the meaning of the intensity here means the power are separate on the whole surface, and then you only detect this point. So this is a PS over 4 pi r squared. And of course this intensity is actually this one, so you can just have PS over 4 pi r squared equal this value. Okay, so let's see this sample problem to see what can we use this equation to do. Okay, so it says when you look at the North Star, the Polaris, 北极星 Polaris. So you intercept light from a star at distance 431 Ly is a light year, 光年 and emitting energy at rate of 2.2 times 10 to the third times that our sun, P sun is this power. Neglecting any atmosphere absorption, find the RMS value of the E field and B field when the starlight reaches you. Okay, so yeah, so first of all we can calculate the intensity. Yeah, so I equals PS over 4 pi r squared. And then it equals ERMS square over mu naught C. So we just make use of this equation and this equation, so they're equal to each other. Okay, and now we would like to find out. R is actually 431 light years, so we need to transfer it back to meter. So we need to multiply it by the speed of light, 3 times 10 to the 8th. So this is the speed of light. And then when 431 times 3 times 10 to the 8th power, so yeah, it is like a meter per year. Yeah, meter. So this is a meter per second. This is light year, which means that light year. So it means that when the light goes for 1 year, this is the distance. So we need to multiply it by, so it's like a year, speed of light per year. Okay, so we need to multiply it by 3,600 to convert it to hour, and then times 24. So yeah, from second to hour, from hour to day, and then times 365.25. Although we generate there are 365 days per year, but considering the leap year, so on average, every year has a 365.25 approximately days. Okay, so this is actually 4.08 times 10 to the 18th meter. Light year. Okay, so actually we can slightly rearrange the term. Actually we need to find ERMS. So we can rearrange the term. ERMS equals PS times mu naught C over 4 pi r square, and then take the square root. Okay, so this is PS. PS is the Polaris. So this is 3.9 times 10 to the 26 times 2.2 times 10 to the 3rd power. Yeah, because we consider. So we consider we are here. We are the Earth. And then the Polaris. Okay, so this is the R. And then this is 2.2 times 10 to the 3rd power P sun. Okay, this is the power. And then yeah, you transmit up to here. And then times mu naught over 4 pi is 10 to the 7th power, 10 to the negative 7th power. And then times 3 times 10 to the 8th power over R square. R is 4.08 times 10 to the 18 quantity square, and then take the square root for the whole thing. Okay, so in that sense, we have 1.24 times 10 to the minus 3rd power. You can use a V over M, volt per meter, or N over C. Hope you still remember the SI unit for the E field. And then BRMS will be ERMS over C, because we have EM over BM is C, so EM over square root of 2 all over BM over square root of 2 will also be C, which means that ERMS over BRMS is also C. So yeah, so this is the case. So plug in the number, we have a 1.24 times 10 to the minus 3rd power over 3 times 10 to the 8th. So this is actually 4.1 times 10 to minus 12 Tesla. Okay, so in that sense, we can determine the root mean square ratio or the magnitude of the E field or B field. And then here we also talk about the radiation pressure. The radiation pressure is related to the intensity of the light. So it says when a surface intercepts the EM wave, EM radiation, a force and a pressure are exerted on the surface. So if the radiation is totally absorbed by the surface, the force is F equals IA over C. So you can feel like if we have some spotlight shooting on you, then you feel like you're actually exerting a force. Okay, so here this is actually the quantity of the force, which is proportional to the intensity and also proportional to the surface area. And then this factor is actually the speed of light, so it just multiply. So here, I is the intensity, A is the surface area perpendicular to the path of the radiation. And then so if you totally absorb the radiation, then the force is 1 times IA over C. But if the radiation is totally reflected, we have a factor of 2. Okay, total factor of 2. Because it feels like, suppose this is an object absorbing the light. So if the radiation come to here and then it is totally absorbed, so it accepts the force will be IA over C. But if it is totally reflected, which means that originally the light is transmitting to here and then you totally reflect it. Okay, so it feels like it has F equals IA over C for the other case, and then the force acting on here will be like 2 times IA over C, something like that, because the light is totally reflect. So it's somehow like the conservation of the momentum. Okay, so it also defines another variable called the radiation pressure. So the radiation pressure is the forces per unit area, so that we just ignore the A term. It only related to the intensity. Okay, so we do not go deep into here because actually I don't know too much about this. The point to introduce this part here is just let you know that this is a property related to the particle property, which means that the EM wave or the light actually has some property of the particle, because the force is of course related to the particle rather than related to a wave. And actually in the later part we also tells you that the light also has property of the wave. Okay, so this is the first one, which is about the polarization. The polarization is quite interesting. Actually, we just let you know some equation, but actually the phenomenon behind is very complicated. I think it is related to some quantum characteristic. So yeah, I do not try to go too deep, just let you know how to calculate some of the problem related to the optical filters. So I think it is quite enough. So here it talk about the polarization, 极化, 极化. Okay, so EM waves are polarized if their E field vectors are all in single plane, called the plane oscillation. Light waves from the common source are not polarized. That is, they are unpolarized or polarized randomly. Yeah, polarized randomly actually means unpolarized. But sometimes we will make the light to be polarized. Okay, so and if the light is called polarized, which means that the E field only point to one direction, something similar to this case. So all the E field point to the right direction, and then all the B field point to the Z direction, and then they just oscillating in phase like this. And then in that case it is pointing to the right side, because you can consider E field pointing to the right axis and then B field point to the Z axis. So E cross B point to the X axis, which means the right side in this figure. Okay, so in that sense, if you just see it from the right side to the left, from the positive Z axis, and then you look at the EM wave, you'll see the E field is only propagating along the Y axis. And in that sense, we call it polarization. And if the EM wave is not polarized, which is like this case, so unpolarized light headed towards you, the E field are in all directions in the plane. So there are some E field pointing to the oscillating along this side, along that side, along that side, so on and so forth. And of course, if it has a E field pointing to this side, it should also have the B field perpendicular to it. So yeah, I don't try to draw it all out, but yeah, every E field should have a perpendicular B field correspond to it. And yeah, actually in this case, we have E field oscillating around different axes. Then we call it unpolarized or randomly polarized. And of course, we can try to gather the E field in probably perpendicular direction, like a Z direction and right direction. So we try to group it together so that it has a horizontal component and also vertical component. Then yeah, it also means that this EM wave is unpolarized. It has both horizontal component and vertical component. For this one, it has only vertical component, or maybe for polarized EM wave, it can be polarized horizontally instead of vertically. But if it has both components, then it is unpolarized. Okay, so here we have another page about the polarization, and of course it is related to the filter, polarizing filter or optical filter. So here it says if the original light is initially unpolarized, the transmitted intensity I is half of the original intensity I0. So it's like I, which is the output intensity, equals half of the I0. I0 is the input intensity or the original intensity. So you can just check out this figure. So we have the incident light rate from the top right, Okay, so come to the bottom left. Originally, it is unpolarized, so it is indicated by this perpendicular line, and then with 4 arrows. So this is unpolarized light, and then this is a polarizing sheet or polarizing filter. So this means that only the vertical component can go through this polarizing filter. Only horizontal component can go through this this polarizing filter. Okay, so finally, only vertical component go through, and the horizontal component are all blocked by this filter. Filter, we can call it filter. Ooh. Ooh. Or we can call it a filter. Filter. Okay, so only the vertical component can go through. Or maybe you try to rotate it horizontally, then only horizontal component can go through. Okay, so this is the first case, which is simple, and you can simply imagine that half of the energy are horizontal, half of the energy are vertical. So only half of it can go through. So the intensity become half of the original. Okay, so the second case is that if the original line is initially polarized, and then the transmitted intensity depends on the angle between the polarization direction of the original light and the polarizing direction of the sheet. Okay, so here it assumes that if the original incident wave is already polarized, and then it has an angle theta with the polarizing filter, so this is the angle. Okay, originally the intensity is I0, but it is already polarized, and then it go through this one. So in that case, the output intensity will be I0 multiplied by cosine square of theta. So it's simply like only the vertical component can go through. The horizontal component cannot go through. But originally the E field is not vertical. So it has some z-axis component and y-axis component. And in that case, only y-axis component can go through. So it multiplied by cosine of theta. So why we have a square here is that because I is proportional to the square of ERMS. So we have a square here. So which means that this EY is E cosine of theta. So and I is proportional to E square, ERMS or EM, both are okay. So we have a square here. Okay, we have a sample problem here, but maybe we just stop here today, and hope you have a happy Easter holiday.